system, bank consumer, and or again environmental studies and so on. Now this is the flow chart how our distributions comes. Okay, so first of all, QLindley distribution. Now we adopt some exponentiated techniques to apply to propose some new distribution. Okay, then some mathematical and reliability properties are studied. Again, some actuarial properties also we have studied. So entropy, actuarial methods, these things are there. Next, to suitability of the proposed distribution to compare with some other distribution, we have applied some, used some parameter estimation techniques also there. Again, some simulation studies to what in case of when we are going to derive some theoretical distribution or theoretical model. So simulation studies is mandatory. Okay, so that's why simulation studies is also there. Then real life applications, and finally what performance comparison and conclusions. So this is the whole my presentation in very brief. Okay, now you see how that particular distributions come. I'm not going to discuss in detail, but simply that the equation number 6, this is my proposed distribution. Okay, this comes with the help of some exponentiated term, and this term will come from what? Their respective distribution function. That is why I have already given what are the distribution function of QLindley, and our exponential distributions. Okay, so with the help of that particular distribution function techniques, so we have what? Derived that our QLindley distribution, exponentiated QLindley distribution, and equation number 6, and this is the PDF of the QLindley distribution. And these are the different shapes. Okay, different shapes with different choices of parameters. In case of QLindley distribution, alpha and theta are the 2 parameters. Okay, now with the different choice of parameters, we have plotted this particular PDF. Okay, and these are the different shapes. Okay, I'm not going to discuss in detail of the particular shapes, but you see here, once you plot that particular distributions, here you observe that it has different types of shape. Sometimes it exponentiated, sometimes it is bell shape, like many things. Okay, so that is why from that particular graph we are able to say this is flexible enough to that other distributions. Others means their Lindley counterpart. Okay, so I have already interpretation is, I think, not necessary. So these are the survival, hazard, and reverse hazard rate functions. Okay, so generally what Sx, that means survival function, is nothing but 1 minus their CDF, 1 minus the form of the CDF, and this is the form of what? Survival function. And next is hazard function. Hazard function is nothing but PDF divided by their respective survival function. This is the hazard rate function. And a reverse hazard rate function is a PDF divided by their respective distribution function. And this is the form of the reverse hazard rate function. And these are the graphical representation of that particular 3 diagrams, 3 forms: survival function, hazard rate function, and reverse hazard rate function. And these are some values. With different choices of parameters, and I have just like the tables. Okay. Now you see, so the hazard rate plots demonstrate the flexibility of the equal distribution under defined parameters values. Okay. Now if you observe that hazard rate or reverse hazard rate, whatever, so that part, sometimes we have seen that particular diagrams looks like bathtub. You know, I think you know bathtub. What is bathtub? So once you get a bathtub type shape, some survival function, then it has very many applications. This type of distribution has many applications in reliability as well as actuarial science. Okay, so I have already. Sometimes we have to get some bathtub shape curve. So it has some many application in reliability as well as actuarial science problem. Now, this is the quantile function. So quantile means inverse of the CDF, inverse of that particular CDF. So our QP, that means quantile function. With the help of quantile function, we are able to draw the data, we are able to draw the sample from our proposed distribution. And this is the quantile function of the same. Okay. Now, with the help of that quantile function, we are able to generate data from that particular distribution. And this is the algorithm. Okay. So once you put that particular algorithm to Python or R or any software MATLAB, okay, then you are able to draw some data from that particular proposed distribution. So proposed distribution means equal distributions. So this is the algorithm. I'm not going to discuss this particular how that algorithm works, but this is the algorithm. Okay. So with the help of algorithm, we can draw the data from our proposed distribution. Next, these are very basic things. Quantile function, first quartile, sorry, median and second quartile. These are plots of that particular three quartile distributions, and with that different choice of parameters. Okay, that means first one is alpha equal to 0.5, alpha equal to 1, alpha equal to 2, again alpha equal to theta equal to 0.5, theta equal to 1, like that. So these are some descriptive statistics thing. And next is okay. Next part is moments. Once you develop a particular distributions, so obviously what we have to determine some moments. Moments means it may be first moment, second moment, whatever, and raw moment or central moment. But here I have this derived the first raw moment of that particular proposed distributions, and these are the raw moments. Though it looks very complex figure or complex in we are not able to get that particular complex form, but though it has a not very complex function, we are able to actually capture the numerical values of the same. So with the help of I think numerical values, so these are some numerical values of the proposed model. Proposed model means proposed proposed moments of the particular proposed distributions. So different sorts of parameters you see. So these are the means. If you put alpha equal to 0.5 and theta equal to these are the values, then mean is equal to this one, variance is equal to this one. Okay, and again coefficient of CV means coefficient of variations, kurtosis, skewness, everything will be there. So I have given the particular tables. As we are not able to find the complex form of the system. Now, these are the reliability properties. So these are widely applicable in industry people, widely applicable in some process control or quality control, whatever. Okay. So first of all, mean inactivity time. So this is a function. First, let me know when we have to finish the lecture. Sir? Excuse me, sir. At what time we are going to finish? Within 10 minutes. Okay. And I have to go faster. Okay, no problem. So 3:15. Okay, no problem. Okay, no. Okay, no problem. I'll try to finish my lecture on by 3:15 also. Okay. Now these are some reliability properties. So mean MIT, mean inactivity time, and some formulas are there. So I've given the last part, okay, but in between them there is a very complex mathematics will be there, mathematical algebra will be there. So however, I have given the last part only. So this is the mean inactivity time function, and next one is the mean residual time function, and these are some numerical values of the same, that particular functions. Okay. So I'm not going to discuss in detail how what the exact particular values interpretations. Okay. So with the help of that particular two table, we are able to say that what is a MIT or MII whatever. And these are the plots. Okay. Now reliability aging property. So this function is very much applicable in the lifetime data analysis. when we are going to study some survival analysis, survival data time analysis. So this function has very much important. Okay, so this is the reliability aging intensity. So simply you can say RAI. Okay, and these are some numerical values. You see, these are the numerical values of the same. Again, these are the function. This is the function. The function is not very much complex. Okay. Next is stress and reliability. Stress and reliability. Suppose X and Y are two component. You can assume that X is a stress and Y is constant. Then probability of X less than is Y. This is test and reliability. Okay, and with the help of this, here I have even given the U and V, whatever, X and Y, maybe X and Y also. So with the help of this, we are able to find out the stress and reliability. And this is applicable again in industry people. And this is the entropy measure. Entropy is essential when we are going to say that the information of that particular distribution. Maximum entropy means maximum informations. So these are some entropy measure. So there are two types of entropy, not like exactly two types. There are many types of entropies. But here we have defined only two types of entropy. One is Shannon entropy, and one is Rini entropy. Okay, so these are functions, and with the help of that particular function, we have calculated this one. And these are some diagrammatic view of that particular Shannon and Rini entropy. Okay, and this is the table, some numerical tables. So actually, what numerical table gives some better visibility. Okay. So now, next is actuarial measures. So first one is value at risk. So this is one of the measure. So this is nothing but what? F inverse of P. Distribution function, inverse of the distribution function. So this is value at risk. And next is one tail value at risk. So there are two functions. And here we have to take some expectation of conditional expectation, actually, just like conditional expectation of this one. And these are some figures of that particular two, VAR and TVAR, tail value at the risk of our proposed model. And these are the interpretation. I'm not going to explain. Now see. Now, once you have a particular distribution, once you have a particular new distributions, then next our main intention is to what? We have to estimate the parameters. Sometimes a particular distribution has 2 parameters, 3 parameters, 4 parameters, 5 or 6, whatever. Okay, but in our case, our number of parameters is 2. Okay, now there are different estimation techniques are there. So out of this we have adopted only this one. Total 7 numbers of estimation techniques: maximum likelihood estimation, maximum product spacing estimation, ordinary least squares, weighted least squares, Kramer von Mises, and Anderson-Darling, and maximum spacing, absolute difference techniques. So with the help of that particular 7 estimation techniques, we have actually what? Estimate the particular parameters of the proposed distribution. So this is the main idea. So when we have to adopt that particular estimation techniques. Okay. Now next thing is there are two types of estimation. One is classical and another is what? Bayesian. Okay. Now this is the Bayesian estimation technique. So here we have to assign some prior distribution. So we were going to estimate some new distribution, say X. Next, once you are going to estimate with the help of Bayesian estimation, some prior information will be there. So with the help of this, I am estimating this one. So again, for Bayesian estimation, Markov-Chain Monte Carlo logarithm is adopted here. Okay. And we have estimated some classic confidence interval as well. So bootstrap confidence interval we have applied here, find out here. Okay. So these are the bootstrap technique algorithm for how to estimate that bootstrap confidence interval. Next, simulation study. Okay. So In that case, all the 7 estimation techniques has been applied here to simulate that particular data of different sizes, and sizes are 30, 50, 100, 200, and 500 as well. And these are our simulation results. So generally, what once if you increase our data, if you increase our sample size, obviously what we will get the decreasing bias, increasing sample number. That means decreasing the bias or decreasing the MSC or standard error as well. And different techniques here. First one is ML, maximum likelihood estimation, maximum spacing estimation, ordinal squares. Different techniques are there, and consequently what our bias and MSC will be there, okay, with the different choices of parameters. So these are a simulation table, and to draw this data we have adopted R software, okay, R is the NSA package. So these are the different types of simulation tables. Now obviously what, as the number of sample size increases, our bias will be decreases, so which is obvious, okay, but we are going to check it. That means what is, if this happens, our model is stable. We can say our model is stable. Our model will get some consistency result, or we can say our model will give some parameters of the particular models will give some property, just follow some properties like consistency properties of maximum likelihood estimation. So we are going to test some real life application of the same. So to model selection criteria, here we have used AIC, archaic information criteria, BIC, Bayesian information criteria, case statistics, and their respective p-value as well. Now we have considered here 4 data sets, and that particular data sets I have given from getting from some literature. Okay, first data set is reliability data. Okay, so these are a description of that particular data, and second data set is service system data. Third data set is environmental data, and the last data set is COVID-19 data. So all the information I have given some link here. So you'll get the details of the information of that particular data set. You'll get it from that particular link here. Now to demonstrate some descriptive statistics of the same, different types of diagrams will be there. So I'll show the diagrams. Just what time comes in, I'm going to first one. Okay, so these are the data sets, descriptive statistics of the 4 data sets. Descriptive statistics of 4 data sets along with some descriptive non-parametric diagram as well. Okay, so these are the sets, and let's have that particular data set. See, some diagnostic plots are there. Okay, so PP plot, fitted CDF, everything will be there. Okay, now these are the estimated tables. Okay, generally if the number AIC and BIC is smaller than the other comparative model, then your model will be set to the beta fitted. Okay, but in that case EQL is our model, our proposed model, and if you observe AIC, BIC is smaller than the other model, that means our model is performs well. Our model performs well as compared to the others. Similarly, if the case value, case means Kolmogorov-Snedding's value, is lower than the others, we can say our model is also better, well fitted. If the p-value is greater as compared to the others, then you can say your models will perform well. Okay, so all the 4 conditions here will display here, which can say. So this is the first data set, and these are the second data set, third and fourth. Okay, so I'm not going to details whatever I have said, all are given here. So I'm not going to the in details. So there are sets, fitted model. You see, so black one is our proposed model. Black diagram is our proposed model. This one, and these are the profile likelihood, and different sets are there. You can check for the defined data sets. And for different estimation method, so these are our results. And now next thing is bootstrap confidence interval. So this is under Bayesian analysis. So I have considered a particular bootstrap confidence interval for all the parameters. So the same conclusion can be made from bootstrap confidence interval as well. So these are Bayesian inference for the all the 4 data sets. These are the results. These are a test plot. Once you find out the Bayesian inference, Bayesian direction will be there. So obviously test plots will come. These are some test plot for Bayesian inference. Okay. So for all 4 data sets, this is the posterior plot. Okay. These are a contour plot. So these are some diagnostic plot for all the 4 data sets. Now, next thing is likelihood ratio test. So this is what, suppose I'm considering that a particular data set comes from that a proposed distribution or not. Then we have to adopt that likelihood ratio test. Here we have applied that particular likelihood ratio test with the help with what QLindley distribution as a nested model. So these are our results for all the 4 data sets. These are results. So based on the p-values, we can say that particular 4 data sets comes from our data set, comes from our proposed distribution only. So now I come to the conclusion part. So first of all, in this talk, in this topic actually we have we have developed a new distribution. This is exponentiated QLindley distribution, and studied some of its statistical as well as distributional properties of the same. And finally, to check the suitability of the proposed distribution, we have considered 4 real-life data sets, and based on that, we are able to say that our proposed model, is one of the competitor of some other well-defined distributions. So that's all my presentation. Thank you. So these are my references. Thank you.
Thank you, sir, for your nice presentation. Any queries or any question from our audience? Any question from the online participants? Any questions? Any question? Sir, one more question from myself. You have mentioned one algorithm. Okay. Have you calculated any time complexity of your algorithm?
Yeah, we can. Yes, we can check the precision as well as time for in that particular algorithm. But main thing is that it depends upon the computer to computer. So in our Dibrugarh University, actually one SPCC is there. Okay, high configuration. That means machine will be there. So once you do that particular machines, so within a very point something second, 0.000, I have to check exact values. I forgot it. 0.001 or 2 like that. 2 seconds, you will get the result. And the accuracy is calculated that particular machine is, I think, 97 or 94%.
That means you have used SPSS.
Not in SPSS. I'm using RS.
Okay.
And you get the same algorithm you can operate in Python also.
Okay. In one more, you have chosen alpha 0.5 0.5, 1.5, like that. On what basis?
No, no, sir. Sir, actually, alpha is always greater than one.
Yeah.
Now, if greater